Can you speak louder?
Yes.
아, 여기 있다. 됐다. 자, 우리 오후 시간 시작하도록 하겠습니다. I am so glad to announce the the continue the special lecture 3. Okay, the special lecture, okay, will be given by Professor Ying-Yi. Ying-Hong is the professor. Yes, next slide is. Yes, I'm sorry. The previous. Okay, he will speak the fault detection, classification, and location by static switch in microgrid using wavelet transform and Daguchi based artificial neural network. Okay, he's next slide. He's a professor at the Department of Electrical Engineering, Chung Christian University in Taiwan. Next slide. Okay, he received the Bachelor of Science and Master degrees from Chung Christian University and the National Chung University. Okay, Taiwan in 1984 and 1986, respectively. Sponsored by the Minister of Education, ROC, he conducted research in Department of Electrical Engineering in University of Washington, Seattle from August 1989 to August 1990. Okay. He received a PhD degree from Department of Electrical Energy and the National Tsinghua University, NTHU, Taiwan, in December 1990. He has been the CICO since 1991. Professor Hong is a IEEE senior member and IET fellow. He was a chair of the IEEE Power Energy Society Taipei chapter in 21 and 22. Okay, he was a vice chair of the IEEE Taipei section. Okay, he received the Outstanding Professor of the Electrical Engineers Award 2026 from the Chinese Institute of Electrical Engineers, Taiwan. Okay. Oh, long. Okay. His areas of the interest are power system analysis and the AI applications. From the 26 to 2012, he was Dean of College of Electrical Engineers and Computer Science and CYCU. He was promoted to be a distinguished professor in 2012 due to his exceptional performance in research, leadership, teamwork, and international collaboration. At present, he serves of the Dean of Office of Research and Development of CYCU. Actually, he is now is Vice President of CYCU. Thank you so much, Ying-Hong. And so you keep your time. Okay, 50 minutes. I would like to suggest 45 minutes. 5 minutes is
Okay,
for the
45 minutes.
Yeah, no problem. Okay, okay. Thank you so much. Please.
I would like to thank Professor Choi for his introductions. It's a real honor for me to have this opportunity to give these spectral lections in this afternoon. So, can I control the slides? Possible? Can I control the slide? PPT. Can you show my PPT? Good. So how can I control my PPT? Can I control myself? Can I control my PPT? Okay. So I would like to give this lectures in 4 parts. The first part concerns the power system resilience versus microgrid. And then the second part deal with the proposed method. In the proposed method, I would like to introduce discrete value transform and Takushi method and detection, classification, location modules in a microcontroller. And then I will introduce the real-time digital simulation, and I will give the details on how to implement a microcontroller. And this microcontroller is based on the Relations RX62 microcontroller. And then the third part is related to the test result. Finally, I will give some concluding remarks. Next page. Okay, storage is okay. Electrical power system is straightened by extreme weather event and nature disaster. Especially, there are many typhoon and earthquakes, and these natures are in Taiwan. And this nature disaster include the typhoon, hurricanes, tornado, and flooding, sea level rising, earthquake, and tsunamis, and so on. And in Taiwan, quite often, it's very common. We have a typhoon and earthquakes. Here, I would like to give an example. It happens on September 21, 1999. The tremors measures is 7.3 on the Richter scale. And in this earthquake, there was more than 2,400 people was killed and 29 people missing. And a lot of buildings collapsed or damaged. And in this earthquake, there are more than 600 electrical towers were destroyed. And it's very serious during this earthquake, 17 substations was destroyed. And at the time to restore the power supply in a large city, it took 1 week. And in the rural area, it took about 2 to 3 weeks to restore the electrical power. In the following, I will give you some photo to show what happened, what is the result after the earthquake. This photo shows EHV substation was destroyed, and we cannot provide electrical power to most of the people. And this photo shows the track around a sport ground, and this track become distorted. We cannot use that. We cannot for the young people to do their exercise. The following photo show the building. The building will collapse. And the following picture show the bridge. And this bridge collapsed after the earthquake. According to the April in the United States, this institute suggests there are 4 dimensions to enhance the power system resilience. The first dimension is generation system. However, it's very expensive. It costs a lot of money to enhance the resilience in the power system. The second dimension is a transmission system. It also costs a lot of money. We have to spend a lot of money to enhance the transmission system. And the third dimension is distribution system. And the last one is customer size. In the customer size here, we want to address that there are several approaches to enhance. For example, the first one is the community energy system. We can install the energy storage system in the customer size also have an electrical vehicle or installed a photovoltaic array in the customer sites. Especially here in this lecture, I would like to address is the microgrid. So how can a microgrid enhance the power system resilience? A microgrid can change its grid-tied mode to identity mode once extreme condition curve. And also the microgrid can also deploy the local remedial actions in the identity mode. And the utility company can develop a restoration strategy using microgrid after blackout. So what is a microgrid? A microgrid is a local energy grid with a control capability, which means that it can disconnect it from the traditional power system and operate autonomously, according to the Department of Energy in the United States, their definitions. So here I want to give an example. For example, at the right-hand side of this PPT, we have a microgrid, and this microgrid have four feeders: feeder A, feeder B, and feeder D. So feeder A and feeder B and feeder C are critical feeders. So if there is a fault, a curve in the grid side here. So if we have a static switch, will connect microgrid, the critical filter from the power system, and the filter A, filter B, and the filter C can still provide his local load power to his local load, even the power system power failure. So the purpose of a static switch is utilized to isolate the microgrid from the power system in case any abnormal disturbance, like a fault, occur caused by the typhoon or caused by the earthquake. Some people use electronic device to develop the static switch. So some people use a circuit breaker, and some people use silicon control device, electronic device, and some people use IGBT, is a high quality, high power electronic device to develop their static switch. So in the past, we developed a static switch in the past. About 10 years ago, we used FPGA to develop a hybrid intelligent system. This hybrid intelligent system is based on the adaptive network fuzzy inference system. The performance of this static switch is very, very fast, but it requires a lot of chip memory. And around 5 years ago, we also used a Linux FPGA to develop another hybrid intelligence system. And we developed a Takashi Sugano-Ken reasoning approach to do to realize this static switch. The performance is also very fast, but it still requires a lot of memories. So at this stage, we develop the third generations. It's based on the microcontroller. We use Renesas RX chip, and we just implement a simple multi-layer neural network. The performance is also very fast and require not many memories in the chip. So in the proposed method, I would like to introduce the discrete Weather transform first. So the purpose of discrete Weather transformed, we use this to do the fault detection and to calculate the faulty voltage and the current value are. Here is the table to show the difference between the Fourier transform and the Weller transform. It's a little bit complicated. I'm not going to details of this table, but here I want to address that if we want to study a theoretical function, we can use the Fourier transform. If we want to study a transient function, we have to use the Weller transform. That's a critical information from the transient signal. So his page show if we have a continual function ft, and this function can be expressed in terms of scale function, left function. Coefficient for the scale function is we call coefficient, and the coefficient for the Weller function we call the detail coefficients. So if we want to calculate the entropy of a function, we can this function, the entropy, can be expressed in terms of sum of c squared plus sum of d squared. The second term of the entropy of this term is Weller entropy. Weller entropy provides very important information from the power system transient signal. The next page shows you how to attain the detail coefficient. The detail coefficient here we need is D1, D2, and D3. How to attain detail coefficient? Here we use multi-resolution analysis. But we have an input signal. The input signal is C0. And then we use high pass filter and low pass filter to attain D1 and D2 and D3. There are 6 sample points for the C0. And the D1 will have 32 points. D2 will have 16 sample points. And D3 will have 8 sample points. So this table shows you how to calculate what is the frequency band for different scale, different D2 and D3s, for example. The D2 now frequency band of the D2 cover 1.92 to 3.84. D3 cover the frequency band 0.96 to 1.92. These two frequency bands cover the transient signals in the power system. The other frequency bands we don't care because they are harmonics in the power system. So what is the Takushi method we are going to use in this research? The purpose of Takushi method is used to provide orthogonal data set for training the artificial neural network in order to reduce its training time, while the accuracy of the artificial neural network still remains. In a traditional design of experiment, possible combination of all factor label we call is 4 factorial combinations. For example, if we have 4 design factors and each design factor has 3 labels, then the number of 4 factorial experience is 81. So we have to spend a lot of time to do the experiment. In this example, we have to do 81 experiments. So if we consider this figure at the right-hand side, for example, we have 3 design factors: variable 1, variable 2, and variable 3. And each variable, each design factor have 2 labels. So we only have to do 4 experiments And these 4 experiments are orthogonal. So we don't have to do 8 4-factor experiment. So we can reduce almost 50% times to complete the and get critical information from only 4 critical orthogonal experiments rather than 8 experiments. But for the next page, suppose we have 4 3-level factor and the number of orthogonal here is only 9 rather than 81. So in the following table, this table actually is orthogonal array. Suppose we have a denied factor A, denied factor B, and a denied factor C, and a denied factor D. And each denied factor have 3 labels. So based on this orthogonal array, we only do 8 orthogonal experiment. So what is the property of this orthogonal array? We have 2 properties. The first one, a column contains the equal number of all labels. For example, the relevant column in the table 1 include 2 ones and 2 twos. Okay? And all combination label in any column appear an equal number. So we can try and to test these 2 probability properties. The Takushi provide a lot of orthogonal arrays, so we can use all the orthogonal arrays in the Takushi library. What we want to study is like a microgrid at the right hand side. Per point side here, power system. In the microgrid, we have 2 long. At the left hand side, we have a long A, and the right hand side, we have a long B. In this microgrid, we have a wind turbine. We also have a battery. We also have solar power to provide the local load. So when we use the Takushi to study this microgrid, we can consider it is the time to design the experiment. We can consider load label, wind speed, and the solar irradiance to show power system.
Your voice sometimes.
The fault may occur in the power grid side. The fault location may be we have
please, excuse me. Sometimes your voice is some stopped, and so I would like to suggest the moving the mouse is minimized. Okay, because the reason is come from the moving mouse moving. Okay, yeah.
Means
some stuff, yeah. Yeah.
Okay. Sorry.
Slowly, yeah. No, very good, very nice. But it's some slowly and moving the mouse is so will be minimized. Okay. Yeah. Please. Okay. Continue. Thank you.
Okay, closer is okay right now?
Good.
It's okay?
Yes.
Okay, sorry about that. So here, I want to repeat here from this page. We have a microgrid, and this microgrid like this, the right-hand side. The upper part is the grid side. The lower part is the microgrid. In the microgrid, we have long A and we have long B here. So in this microgrid, we have a wind turbines, and we also have a solar power and a battery. So if we consider this microgrid is a system, then we need to design the experiment Okay, so the design factor is low label, wind speed, solar irradiance, and short circuit capacity. Now we have to consider location. These fault locations are input to the system. The fault may occur in the grid size. The fault occur in long A. The fault may occur in the long B. Then we also have to consider noise. Noise is the fault type. We have to consider balanced fault. We have to consider unbalanced fault, like a single phase to the ground, double phase to the ground, unbalanced fault. The phase output. Output is wavelength entropy of a three-phase voltage and current and the neutral current, for example. Here is the design factor. We have a four design factor in the following table. In this table, factor A is the low label. Factor B is the wind speed. D is the solar irradiance. Factor D is the short circuit capacity. For each design factor, we have three labels. We assume we have three labels. So based on this design factor and the label, we have to carry out 9 orthogonal experiments. So for a given set of factor, one experiment, we have 340 location and the 11 types of fault we have to consider. Currently, we have 33 scenarios. Because we have 9 orthogonal experiments, we have to do 297 40 scenarios plus 9 normal scenarios. So in total, we have to do 306 scenarios. We have to produce 306 scenarios to train an artificial neural network. If we use factory experiments, then we need more than 2,700 scenarios to be produced to train the neural network. So the number required data set for training neural network can be reduced by almost 88.9%. So we can save a lot of computation time. So the next one I want to introduce is classification location module microcontroller. All we need is a three-phase silicon control rectifier switch and the main circuit, signal sampling, and the power supplied for the hardware. So in this study, we require only voltage and current signal, 7 signals in total. We will measure this voltage and the current signal by potential and the current transformer near the local static switch. So in this study, we developed 5 modules in the microcontroller. The first module is 3-level discrete transform. Module is wavelength entropy. The third module is to calculate the difference of voltage wavelength entropy. The fourth module is to calculate the difference of current wavelength entropy. The last one, most important one, is artificial neural network here. So this page shows the artificial neural network. We have 7 input to the artificial neural network. We have 7 output for the neural network. For example, if we have output, the output is 0, 1, 1, 1, 0, 1, 0. This means a balanced two-phase to ground fault occurred at long A. Okay, and this unbalanced phase to ground fault is a phase B and phase C ground. The next slide is the real-time distortion. Well, actually, we do not have a microgrid in our lab. So we have to implement the microgrid, including wind turbine, PV array, energy storage, load, and power electronics, everything in a real-time distortion. And here is all the hardware we have in our lab. So we put everything, the microgrid, in this hardware to simulate the fault condition in the microgrid. Here is the microcontroller. So suppose the sample rate is 256 points per cycle for a 6 hertz power system. So in the power system, we only have, in this study, we only use the 64 sample of the signal and use it in C code based Weather transformed, because a large change in the instantaneous values of the voltage occurrence is most likely to happen in 1/4 of a cycle. So the 64 sample can be used in the buffer arrays of a microcontroller chip in implement the moving window. Okay, here is the microcontroller implementation. The weight and the bias of artificial neural network was trained offline by one optimization algorithm using 306 orthogonal training data sets. And the artificial neural network was developed using C code in a microcontroller, and all the parameters are fixed, and all the weight and bias are fixed and trained and considered as a constant. And the proposed artificial neural network required approximately 142 constant. So in the following, I provide a table showed how many resources we use in a microcontroller, and this resource we use including the weather transform and the artificial neural network. Here is the microgrid we started in our research, and we have some result comparison between our proposed neural network and the other measures. In our measures, we can get 100% accuracy, and also we compare with other measures like the decision tree. In the decision tree, we can attain the accuracies around 87% to 89%. And we also use another neural network. We call it RBF neural network. The accuracy is 94% to 99%. The other test is to detect the real-time validation using the real-time distortion. Suppose we have a 3 fault occurred in the long V. And here three scenarios are three-phase fault, two-phase fault, and one-phase fault. The time we can, from this test result, we can find the time to open the switch is around 11 to 13 milliseconds. This time is very short, shorter than one cycle. And this time is required to compute the wavelength entropy of fault voltage current and to calculate the neural network output. And the last test is SCR-based static switch hardware. And the size of this static switch hardware is 50 kVA. It's a real one. It's a real static switch hardware. And we also have three scenarios. And from these three scenarios, we can find the time delay caused by the static switch is around 1.54 milliseconds, during which the fault current declined to 0. In the conclusion, I would like to give the following. This work proposes a fault detection, classification, and localization method for use in a static switch at the point of common coupling of a grid-connected microgrid. The proposed method can successfully disconnect the microgrid from the power system to enhance the power system resilience in case of a fault caused by natural disaster. The novelty of this work is that the Takushi method reduces significantly the number of data sets and solid connected artificial neural network. The advantage of the advantage of the proposed methods. A microcontroller chip is used rather than complicated FPGA or DSP chip. The latency caused by this microcontroller is only 11 to 13 microseconds, and the time delay caused by the SCR switch is about 1.54 minutes. The proposed method outperforms the traditional decision tree and RBF neural network. And finally, I would like to give a comment about research just published in the IEEE System Journal in this month. It's volume 14, number 4 in IEEE System Journal. Okay, thank you for your attention. Thank you so much.
Thank you very much. Okay. Yeah, first of all, the congratulations for me, Professor Hong. Yeah, thank you.
Thank you so much for your attention.
Yeah. Okay. Some question or comment? Please one or two. Please, Professor Wang Sangdi. Okay. Please, one question. I have one question.
Yeah.
Please sliders Opal RT sliders.
Yes, OPRT.
OP560. Yeah, very nice. Looks like micro the wind turbine generator, PV arrays, and storage load converter inverter line. Yes, yeah. And by using this, the Opal, I have heard about this many times. This is simulators. By using this Opal RT, what kind of results can we obtain from this simulator? What kind of results?
You mean what kind of output attempt from the simulator?
Okay.
Yeah, this simulator can generate all the time domain simulation.
Yes.
All time domain the signal, and the output is real time. It's real time. So if we can, for example, when we study a fault, it's short circuit conditions. We can attempt, for example, here. Let me show you microgrid. One figure, the one line diagram. Here.
Okay.
Example.
Where and when?
I measure the current and voltage in a switch.
Okay, very fast.
So we have a 7 output from the real-time simulation. 7 signals.
And the
3-phase voltage, 3-phase current, and the neutral current. So we have 7 signals from the RT.
Yeah.
Yes.
When and where is the grid, microgrid is the disconnected? When, what time? Time or the where is the we can obtain the results of time and place. Is it right?
Yes.
Okay. Yes.
It's time very short. In total, the time delay is less than 20 milliseconds.
Okay.
Less than 20 milliseconds.
Yes.
It's very short.
Yes.
Based on our study.
Okay. Thank you so much. Okay. Okay, one question or another question, comment? Professor, maybe Nakanishi or the...
Yes.
I think this is the... Yes, yeah, Nakanishi. Yes. Thank you.
So, sorry, I cannot catch you. In this your study, do you have many detection point? I mean that the detection measurement point.
Measurement point.
How many?
Here
The system.
Here.
There are a lot of measurement.
Yeah. But I only have one measurement. Only one. Only one near the SS here in this figure. Only one.
Actual system that the deflection, the dynamic wave is rather than more than the 1 kilohertz high frequency dynamics. So that several waveforms deflection that another point to return point. So sometimes it is necessary to put on the several detection point and select to find that deflection waves, right?
So can you repeat?
In your case, the very slow dynamics waves.
But
so
with the problem, we consider only have a transient. So very short time. 那个 dynamic condition, 那个 dynamic phenomena, but it's a very short time. It's a transient state. So we can use the real-time digital simulation to study. So if the problem is a dynamic one, it's a long time dynamic one. So we don't use the real-time digital simulator. So the problem only have a very short time. Then we can use the real-time digital simulator.
That is your condition, assumption. Okay, I understand what it is. Thank you so much.
Thank you.
Yeah, thank you very much. I am feeling your proposed the Takuchi based the OPAR the simulator is quickly decided. Okay, some disconnect time. Okay, very quickly. Very quickly. Okay, thank you so much. And now it's recently I am thinking about is very deeply is how much is resilience index, how much level of resilience index, resiliency, how much the typically the resiliency, the curve is the V curve. V is the equivalent of collapse, and the some is recovery, and the typically is V curve. As the coronavirus, the some how is the curve? Is the some curve V area? The area means the resiliency index. I think the smaller is better. Yes, yeah. I some compare by using this your algorithm, by using your algorithm in the I would like to some compare is a typical the conventional algorithm and your proposed algorithm. How much is the V curve is narrow? Okay, yeah, yeah. Index, resilience index. Yeah,
To recover.
yeah.
In our study, I just
Yes,
develop a measure to
yes.
disconnect it only,
Yeah, another.
rather than to recover. That may well be the good study to
Yes,
recover, to restore the power
yeah.
to the and to reconnect to the power system. But in my study, I only study the first
It's right.
step
I understand. Yeah.
to disconnect it only.
Okay. Okay. The Professor Hong, thank you so much for your nice proposed new algorithm published
Thank you.
by the IEEE. Yeah. Thank you so much. Yeah.
Thank you so much for your listening. Thank you.
Yes, yeah. I understand.